Good afternoon. How are you guys doing? Good. All right. My name is Rick Branson. I'm an infrastructure engineer at Instagram. That means that I am sort of in a DevOps role. I write a lot of code, but I also keep things running. I'm giving a talk today called Why You Can't Have That Pony. The idea with this is that I feel like a lot of people talk about why you can't have things like distributed transactions and things like that, but they just kind of throw out terms like cap theorem and things like that. But they don't, there's not a lot of stuff out there that I feel like has a really decent sort of description of sort of taking things through the actual like protocols and the way things work, and talking about kind of where you hit these walls when you run into these problems. So hopefully I can give you some information on that and leave you guys with something important. I saw this tweet today, or it was like yesterday, and it kind of surprised me because, this is obviously a promoted tweet by a company called FoundationDB, which has this supposedly distributed, highly available, fault-tolerant thing. And they have this paper, and it supposedly says that cap theorem doesn't let you do this, or does let you do this, or whatnot. And then you kind of read it, and you're like, OK. It says, as any ACID database, during network partition, FoundationDB must choose consistency over availability. All right, that seems fine. And then you get a little deeper, and it says, this does not mean that the database becomes unavailable for clients. When multiple machines or data centers hosting a FoundationDB database are unable to communicate, some of them will be unable to execute writes. Seems an interesting interpretation of what availability means. It kind of shows you that everybody's kind of got their own definition in terms of that. And this differs from cap availability when you actually read the paper. And they admit it in their white paper. But ultimately, I feel like they're just trying to draw you into this discussion. And obviously, they're trying to sell their product. So let's talk about these ponies. These FoundationDB guys are right. And there have been many people talking about this. There's a lot of the new SQL people are doing this. VoltDB and some of the others are using this sort of, trying to sort of spin these words into saying that they have this high availability. And there are some ways in which you can get this, a lot of these ACID properties, but not in the way that they're actually talking about. And cap theorem is kind of used and abused, as I've demonstrated. It kind of boils down to this. It's the data just kind of gets stale if you can't synchronize it. If you can't talk between two systems that are trying to synchronize data with one another, well, they're going to fall out of consistency. And so it's misunderstood. A lot of people think it's this like pick two of these three, when in reality, I don't know where this came from. I don't know who kind of came up with this idea of pick two. I actually spent a lot of time last night trying to dig and find like a link where somebody like has some legitimate sort of thing behind it other than just saying it. But really, it's just pick one when it comes down to it. So this is your choice. And I think the consistency thing is a little misnamed. I actually prefer the term consensus, because consistency confuses it with like ACID consistency, which is completely different. This has to do with, are things synchronized between multiple nodes? So you lose these things. CAP tells us we lose some of these attributes if we want availability. Strict resource allocation, which is like bank accounts, flight booking, things like that. Compare and swap. I want to say update where, for instance, like in a SQL query. I want to set this value where this value is equal. You can do something like that, but you can't guarantee that the result is going to be, for instance, like if you increment a counter and things like that. You can't guarantee that you're going to get the only person winning that result. And of course, uniqueness guarantees. This all kind of falls in the these same buckets. Global uniqueness guarantees, you have to say, for instance, if you're handing out usernames on your Twitter and you're handing out usernames, you want those to be unique. And an AP system simply can't guarantee that. And also, a CP system can't guarantee that because it gives you consistency. Sorry, I'm confusing myself. This is how confusing some of this stuff can get. The AP system can't guarantee that you have that uniqueness, and the CP system can. However, the CP system is subject to availability problems. And there is hope, and I'll talk about there's some hope, some new developments in Cassandra, some new research that's coming out but I'll talk about this towards the end. Let's talk a little bit about this resource allocation problem. I think it's kind of the easiest one to understand. It's things like hotel booking, financial accounts, warehouse inventories. Anytime you sort of have a restricted pool of resources that you're trying to dole out to people in limited amounts. And so let's talk about it in terms of like the Cassandra model, which is asynchronous replication. And this is very simplified. This is the Cassandra model provides availability over consistency. And yes, it is tunable, but in order to really exploit the properties of availability, you have to use a lower level of consistency. So say we have a client, and we get a balance, and it comes back for $100. We have 2 replicas, each one's storing the balance. If one client says, I want to deduct $75, the first replica says, OK. And at the same time, before it's replicated that change to the other replica, it gives that old balance to the second client. So it tries to do that same deduction. And the result is that both of these end up with a negative balance. Now, yes, I realize that banking, this happens in real life, that banking is a sort of tired example for this stuff because most everybody in this room has probably experienced an overdraft fee because of some consistency problem that exists within a banking system. But this is purely for illustration purposes. So how can we kind of do better? How can we fix this? If we do want to choose consistency over availability, what does that look like when we start digging into this? This is a system that's got 2 replicas. It's a protocol called two-phase commit. Two-phase commit involves a coordinator node. And this is kind of the like system that serializes all of the writes, that sort of aligns these reads and writes so that they're all in order. And everything is hunky-dory. Kind of looks like this. A client would say, deduct $75. The coordinator might say, OK, give me a second. I need to conduct this transaction. And it would send messages to the different replicas. And they would say, OK, I've prepared this transaction. So if another client came in and said, do the same thing while this was running, client on the left-hand side is, that transaction is still pending. And the one on the right-hand side, tries to send one, the coordinator will block. It will not allow that to go forward. That's the job of the coordinator. So the client on the right-hand side is still pending. But now we've agreed, since we got those messages back, we've agreed that, yes, the client on the left-hand side should be able to commit this. And so we agree that the new value is $25. And then that coordinator can say, OK, I failed that because I have a consistency requirement to keep this balance above $0. Pretty simple. It does require all the replicas to respond, which is unfortunate. It means that basically if I can't contact one of the replicas, I'm in timeout mode. It's almost like using Cassandra with a consistency level of all. One failure will cause you to have a problem. The coordinator is also a single point of failure and a bottleneck. So whatever the coordinator is in charge of coordinating, it's the sole system through which you can both read and write data, which is a problem. If the coordinator dies, you're kind of left in this weird state. You can't actually, like for instance in Cassandra, because operations are idempotent, because they do converge, you can retry things. With this system, because you can't make sense of the state without sort of reading everything. You sort of are in this state, and you just have to say, I don't know where I am, and you're in this weird sort of netherland between transactions. You can use a standby coordinator, for instance, to replicate that log. This is, for instance, what they're working on doing with Hadoop, with the well-known name node single point of failure. So you have this synchronous replication of coordinator log. And this is because this is exactly from the two-phase commit Wikipedia article. And basically, you assume that you have stable storage, no node crashes forever, the data is never lost or corrupted, and that any 2 nodes can communicate with each other, none of which happens in real life all the time. If you have a slowdown of that standby, you're now sort of completely hooked together with that standby. If that standby starts slowing down or crashes, things stop. So you're actually more likely to fail because anytime you introduce more nodes into anytime you introduce more nodes into a system, you're more likely to have a failure of any given node. So you can do better, though. There's a system called Paxos, and I'll try to explain Paxos in the most simple way possible, because I think most explanations out there are way overcomplicated. Granted, it says it's still consistency over availability. With this, we have to have 3 replicas. Paxos requires it. You have to have essentially you have to have a tiebreaker anytime there would be a sort of whenever it need to create what's called a quorum. So your client would say, I want to deduct $75. You might reply, pending, just to say, I received your right, and now I'm working on it. It does the first step of this is to do a propose. And the propose tells all of the replicas of this data and all the participants of this transaction to say, OK, open this transaction up. And it doesn't actually tell it what to do. It just simply says, I want to start a transaction. And the return from the replicas is a promise. And the promise says, among other things, basically that I am promising to make you the leader of this round or transaction. And the nodes hold locks after the proposal. So for instance, if this other client comes in and tries to say that, it'll hold that until it finishes. So it'll say, OK, I've already promised this other node that this account is locked, at least until maybe a timeout or whatnot. And it'll queue that operation as pending. The next step, once the proposer has received that, they'll basically send out an accept and say, this value is $25. That's after I take the $100 out of the balance, I now have $25 left. I send an accept out. Now notice we've got 2 pending requests to both of these nodes, and the A is still the leader in this case. It's still everybody's locked, waiting for this transaction that's led by A to finish. And then after this step, we do what's called we acknowledge the acceptance of that transaction. Everybody broadcasts to everybody, so that everybody knows that everybody else has accepted this basically gone through that round. The value in this is that it's very fault tolerant. Obviously, it's a lot of extra work to go through this as well. And most people don't use Paxos for bank accounts. They use it for leader election and things like that, and then they assign a master and things like that. But this is a demonstration for demonstrative purposes. And then it would just simply say fail. Because once it got through that round, it would know that there wasn't $75 in the account, there wasn't $75 in the account, there was only $25, and it would be unable to deduct that from the balance. It's somewhat fault tolerant to node failure. Like I said, it's a quorum base, so it can say that if I have a majority of nodes, I've got A and B already, I can assume that because I have a majority, this transaction can go through. It allows the round to continue. Also, this property of broadcasting the results to everybody in that round, these are considered the learners technically, means that you're also sure that you're not going to get conflicting values at the end of this. And you're not dependent on one node, for instance, the proposer, it could fail in the middle of this. So we need to basically broadcast to the rest of them so that everybody understands the value, everybody agrees on that value. It's still subject to cap, though. It's at first, everybody gets excited. They see Paxos, they see node failure. They're like, oh, this is great, But the problem is that you can still have network partitions, and you still have to choose which side of that network partition. And network partitions are not always just single, 2 sides. They can be complicated. You can have some nodes that can reach others, and then you can sort of have this multifaceted, weird, diamond-shaped network partition. So this is in the simplest case. Node A is trying to propose, and it simply can't talk to the other ones. So anything on node A will fail at that point. And even reads will fail at that point, because it's in a strictly consistent system. You can't guarantee that nothing's changed on the other side of that network partition. You lose. So you do lose your strict resource allocation, like we talked about, like banks, hotel booking, things like that, compare and swap, uniqueness guarantees. Now, that doesn't necessarily mean that the best business decision is to go with strong consistency, but you simply can't, those are the things that you can't get around in terms of from a very technical perspective. And I think if I could reduce these down to anything, it's basically the ability to pick a winner. For instance, in the global uniqueness guarantees, somebody has to win a username. You can't have two people with the same username if that's your business requirement. I'm sure that there might be some intrepid souls out there that allow that to happen, and they, lottery out the number, or they decide, based on some kind of heuristic who gets it, if there's some kind of conflict. But, I think most people would just like to have one username. So consistency is something that's important in a system like that. Can we still get ACID, though? I didn't necessarily put these ACID transactions in there, and I think it's because it's a little bit of a misconception that you can't have sort of these ACID properties in an eventually consistent system, even with distributed transactions. Definitely within a row. So think of a Cassandra row in terms of it's on a single node or a single set of replicas. You can get things like durability and atomicity through the commit log. The commit log ensures that once something's been written to the commit log, it'll continue to get replayed, and you get durability through that. If the process crashes, it'll get replayed, and that's really A and D. You got isolation in 1.1. So now if you do different changes within a batch in Cassandra, you'll see those changes or you won't. Isolation being like if you add 1,000 columns in one batch, you're either going to see the 1,000 columns or not. You're not going to see 500 of those columns get inserted. And consistency, I mean, maybe. It's very loose. Cassandra is obviously not like this really strict SQL-like system where you have these really complex constraints. There are some constraints it could potentially, you could add on to a system like Cassandra. Things like, I want the value to be within these ranges as long as it's not something like a counter where you can have incremental operations. As long as it's like a string, I don't want the string to exceed 255 characters. As long as you're only replacing that string, for instance, you could guarantee that. So what about like cross-row or distributed transactions? This is kind of the holy grail. It's a little more interesting, I think, than just doing sort of, oh, great, I have a row. It's useful for things like if you have a graph database and you want to track both the outgoing side of the node and the inbound side of the node for query purposes. It's really good to be able to have some of those guarantees around, when you do a distributed transaction, making sure that the system will follow through with those things. Consistency, probably really not. I mean, when we think about consistency, we think like foreign key constraints and global consistency, like global uniqueness requirements and things like that. I'm gonna go ahead and say this is, and this is my opinion, that it's probably not really something that is feasible. It is in some ways, but again, it would be only for maybe a value like the string doesn't exceed 255 characters. That's relatively easy to provide, something that doesn't require information from other nodes. Durability doesn't really apply per se. I mean, maybe distributed durability would be like, writing to multiple nodes, but really ACID is kind of a poor choice of term in a way for a distributed transaction, but we'll kind of muscle through it. 1.2, they added atomic batches. I was talking to Matt Dennis, who's with DataStax, and yes, you could have accomplished this before, but it's nice that Cassandra takes care of it for you and actually kind of deals with these edge cases. It kind of works like this. You have a client. It sends a batch to one of the nodes in the Cassandra ring, and that node will actually replicate that batch log to another one, to another node in the ring before going forward. And then it'll do a write. So it'll just write out that batch to all the nodes that it needs to write it to. And the main point of this is that it resists coordinator death. This is the hardest part of implementing this, is if you have the coordinator die, the thing that you sent the batch to from the client, how do you guarantee that it didn't just fail in the middle of that and you've got partial writes and things like that? This is really useful for, like if you're writing indexes of your data, you have like a main column family that's got all your data in it, and then you want to query it in different ways. These are the Cassandra way to do your data modeling. It's a lot harder if you have no way of knowing that transaction is going to finish all the way out. So this is really a really useful system. If it dies like this, for instance, we only got to two of the replicas. It's not on the third. Yeah, all that stuff, the repair and things will fall through. But this is more in terms of I didn't actually make that last write. Like I wrote row number 1, I wrote row number 2, but I missed row number 3. And then basically the batch replica will detect that failure eventually and replay that batch. And the idea is that you get this eventually. It's not atomic in the sense that all of a sudden everything appears at the same time. It's that all of a sudden, eventually everything will be there or it will not. Actually pointed to the wrong thing on this slide. Kind of a rookie mistake. I really meant to point at isolation there. Basically, there's this paper that came out of Berkeley. There's this guy named Peter Bayless who actually wrote the predict consistency code. I think he wrote it in the Cassandra, in the newer version of Cassandra, that can actually do a prediction of exactly how eventually consistent your data is and when can you sort of predict when you'll reach the consistent state. But he's a really smart kid. Made this with some other people at Berkeley, made this HAT paper. HAT stands for high availability transactions. And it describes a way to get eventually consistent transactions with read committed isolation, which is really interesting. Basically, the guarantee is that data won't appear, so you can't read it until it's live on all the replicas. And that's cross-row. So if you need to write like 2 different sides of the same data set, but you don't want that to appear until everything is done, this is a really valuable kind of concept. Again, it's still a concept. It's still something, like the paper came out like a month and a half ago. So people are still noodling on this. It's obviously been published, so it's a little more than just someone's blog post or something. So hopefully this kind of stuff can get in there. It's like, it is among a replica group, so is that a data center? I don't know. It'll be interesting to hear from, once this paper starts to make rounds within the Cassandra community, start hearing about how people think about implementing this in this system, if at all. I'd be really excited to see this. It does still require convergence, though. Ultimately, the property of Cassandra that makes it able to survive outages and survive these things and repair itself is the ability to take conflicts and always converge them reliably. You never are in a state in Cassandra where you don't know how to kind of get back to a stable state, which is unlike you have where split brain issues with master-slave systems and such. So cool. Hopefully this was didn't put you guys too much to sleep. I left a lot of time for questions at the end of this because I had a feeling there would be a lot of them in discussion. So I'm going to open the floor up now for that. He's going to come by with the mic. Yeah. Nope.
Can you talk a bit about what you do with Cassandra at Instagram?
I had a feeling that would be the first question. So we use Cassandra for high write, low read rate data. Most of our data is stored, like our social data, like likes and comments and information about photos and things like that, is stored in Postgres, just a sharded Postgres setup. It's been that way since sort of the beginning. There's definitely been talks of moving things over, but nothing's really kind of solidified because there's just, you have a certain number of hours in the day to kind of get things done. And as the data size grows, it becomes less and less it becomes definitely non-trivial to migrate data over and doing it in a way that makes sense. I mean, we're definitely growing our usage of it though. It's just a matter of finding the right use cases and pairing it. Just specifically the types of data we use it for is like security logs, auditing, and things like that. Spam fighting, that kind of basically stuff that we want to make sure we have and keep, and we don't have to worry about performance problems or outages, and it's very low maintenance for us. Actually, we had a machine die yesterday, and it was like, kind of didn't even realize it until I looked back through my pages and saw that and replaced it, and everything was fine. So. No, most of the data we have there is designed to be permanent. Unless we do permanent deletion of the data, like for instance, if a user deletes their account, we have to go through and scrub all that data. But we try to the idea is to keep this data for around forever. So if you have any more questions about that, I'm fine to also talk about that.
I was curious how the hat paper kind of differs from setting the quorum for the number of nodes on the read.
Yeah, so the quorum in Cassandra doesn't guarantee that you, it does guarantee that you, for a given row that you'll see that, if you read and write with quorum, you'll basically have this sort of read your writes consistency where if you write something, you'll read it back. But what it doesn't guarantee is that if you have multiple nodes inside of multiple rows inside of a batch that are on different nodes, which is very likely, given distribution of a cluster, that you'll actually see those changes in an isolated fashion. So say you make updates to 2 different rows that are on different, completely different partitions. The sort of innovation with hat is that it basically allows you to only see that when everything is finished with that transaction. It's truly like a transaction where you say begin, submit things to push into the data to push into the cluster, and then you'd commit, and then things would be only seen after it's sort of percolated so that everybody would sort of get that instead of just certain given rows.
Could you explain, please, like, in your opinion, what's the difference between Zookeeper and Paxos?
Zookeeper is built on a Paxos, basically a protocol called Zookeeper Atomic Broadcast that is built on top of Paxos. The Paxos that I explained was a very, very simplified version. It's sort of the most simple version to implement. There's several versions that are more complicated that can avoid some latency problems. Zookeeper specifically it basically elects a leader, and only transactions basically flow through that leader, and it uses Paxos to elect the leader. But because the leader is there, it can do some optimizations. It's almost kind of like, in a way, kind of master-slave-ish. If I had more diagrams, I would probably be able to explain it better, but hopefully that answered your question.
So what's your advice for modeling situations where there can be network split and the application may end up with pieces of data that can conflict with each other? Eventually you could have some rules that we recover from that.
Right. So the question is, how do you model your data when you have, for instance, you can have a network split? It really is extremely use case dependent. It depends on your business decisions too. I mean, this stuff has to basically kind of be educated all the way up, because if people don't understand that you have to make that fundamental trade-off, they're going to make bad decisions. They're going to ask you for things like 100% perfect uptime with global consistency, which is impossible. So it's important to educate people in your business about how these things work, and then try to come up with sort of contingency plans on what to do when there's problems like this. A good example is when Amazon oversells their inventory. Now, I'm not sure this is because of eventual consistency problems or not, but they certainly have done it before. I've been there. They send you an email and say sorry, and here's $5 credit or something like that. I mean, that's a way to solve that problem, and it becomes sort of an actuarial problem. It's not a you kind of create a sort of you kind of have to create a formula of like, if we're down for this long, how much is it costing us versus if we maybe oversell a few things or we have to give people $5 gift cards. I mean, it's kind of that choice.
How do you store all the images in Instagram, and have you tried to store all your images in Cassandra?
We use S3, and we have experimented with using Cassandra for it. But I think S3 has just been perfectly fine for us. So it's been actually really kind of incredible how well it's worked for us. So there's not a lot of sort of, the motivation would be to fix things that are breaking or broken or suboptimal, and S3 is definitely not one of those things. But I have sort of experimented with it.
Do you have maybe some benchmarks or some numbers or statistics?
I don't. It seemed to be mostly disk bound. Images are fairly large compared to the average data that's stored in a database. So you end up just disk bandwidth bound and seek bound on your drives. So.
One of the gentlemen in one of the earlier sessions mentioned that Instagram was using flash caches.
We use Flash, yes.
Did you benchmark versus solid-state drive, SAN, and Flash?
Yeah, so we use Flash exclusively for our Postgres. We don't use it for Cassandra because Cassandra is, again, low write or high write, low read data. We push tens of thousands of writes plus probably more now through Cassandra, whereas we may do a few hundred reads per second. So it's really, the write performance is great. I mean, we just don't need SSDs for that. As far as the flash drives for Postgres, we haven't done any I don't think we've done any benchmarking that would make sense to anybody else. It's worked really well for us. Basically, like in a relational database, in order to get any kind of reasonably good performance out of it, you either need a giant drive array, or you need a lot of RAM, or you need SSDs. So, it's the latency. We typically use our sub 1 millisecond latency for most of our queries now. Whereas before, if it was either in RAM and it was getting that, or it was on disk and it was 100 milliseconds or something really bad like that.
I think I've heard a lot of suggestions about how it is possible to achieve multi-row consistency using mostly theoretical mechanisms right now.
Mm-hmm.
So do you care about that? How do you do it? Do you use Zookeeper as a transactional layer on top of Cassandra? What does Instagram do?
No, so the only case where we really need to do this is where you have sort of friendship relationships. And we have been working on a way to do this just using data repair, but not basically doing read repair on the, doing a chance of basically, if you read the friendship relationships out, rewriting it the other direction and checking to make sure it's there. Similar to what, Cassandra, you can set a 10% read repair for replicas, and this would actually be across different rows, not just within a partition. Does that make sense at all? Maybe. Okay. Maybe we discuss this offline.
Hey. Hi.
Hey.
First time, long time. Big fan. Paxos over high latency links, or if you're doing it multi-region, I don't know about your infrastructure. Does it just go off the rails? We use Zookeeper across it, and we have observers in one place.
Yeah, it can. It depends. Paxos is kind of more an idea than a implementation of an idea.
Okay.
There's multi-Paxos and generalized Paxos, and then there's Zookeeper, which is its own version of it. I would say it's generally recommended not to run Zookeeper out sort of with unreliable WAN links. The whole idea is that you can resist sort of small sets of network failures, but ultimately, if your link between two data centers goes down, which is much more likely than inside of your data center, then you're sort of in this state where part of your system is almost is basically not very functional. You also it's weird because you end up sort of spreading. It becomes weird to spread things out. For instance, if you have two data centers, do you put how do you tie break that, right? Some people don't have 3 data centers to always put something in, for instance. So how do you create a quorum and tie break that?
I got 3, so whatever.
Yeah.
No big deal.
Indeed. But to add on to that, I think people that are using it for cross data center use cases aren't using it for data storage or anything like that. I think it's an anti-pattern with Zookeeper and in general to use it for data storage. Sorry? Yeah, for leader election and things like that. I think, I would say generally try to avoid leaders in general, but sometimes you can't. So, you wouldn't necessarily want certain things to get out of consistent. It would cause issues, configuration and things like that. Typically, though, people will set up a Zookeeper sets of zookeepers in different data centers. If they're doing something like consistent configuration, they'll set up a zookeeper, a zookeeper installation in each data center, and they'll basically, use the local one in that data center. I think it's a good pattern.
Hey, concerning about atomicity, I've experienced a problem where there are two simultaneous updates, two batches, and they interleave. They don't guarantee, they didn't guarantee atomicity. And then I researched on that and found the problem probably a Hector package we use, and maybe another version that assign different timestamp within the batch.
Yeah.
Okay, so that's a specific problem. Then now I'm thinking, if we have two different data centers, or even two different JVM, it's very possible to assign the same timestamp. Then that will break atomicity, right?
It won't, because all that's happening then is that the conflict resolution in Cassandra is sort of ruling that out. All the atomicity guarantees is that that batch of operations is applied or it's not. And then the conflict resolution is actually a completely separate protocol on top of that. Basically, those writes will actually still happen. But then once Cassandra actually performs the read, it'll see that one transaction's timestamp is higher than the other ones, and then resolve that.
Yeah, but and also studied the resolution algorithm. They always put delete in front of updates.
Right.
For two updates, they take the higher value in bytes, right? That will make it really inconsistent for two simultaneous updates.
Everything would still reach eventually the same result, though. That's the idea, is that eventually you would every replica is going to eventually receive the same result through the anti-entropy system. So it may not be now, it may not be like in 1 millisecond, but it will be eventual. Mm-hmm.
If you have a batch of 3 rows and a batch of 3 rows.
So, yeah, so, right.
Then your batch atomicity can be broken later on during the conflict resolution, because conflict resolution happens on row level.
Yeah, the conflict resolution.
Let's say you have 3 rows and 3 rows.
Mm-hmm.
All 3 rows will be written for this batch, but then row 3 can be overwritten from another batch because of row level.
Okay, so I'll repeat what basically I think what you're saying. The idea is that the timestamps, because they're at the column level and the data inside the batch, instead of being at the entire batch level, you could have two transactions that would potentially conflict with one another. There's no guarantee within that transaction that there isn't one overwriting the other. I mean, obviously, putting them all with the same timestamp is sort of a no-brainer. Maybe. It depends on, obviously, what you're doing. If they are all the timestamp, then all with the same timestamp. I see what you're saying actually now. Yeah. No, you will eventually get the same result. Right. Right. So are you saying that if one update sees a different update that was there before and how those converge? They will still be applied in order, though, in a way. So ultimately everybody's going to see the same set of. The idea with a dynamo-based system is that everybody eventually sees the same set of replication out at every node, and they're all going to eventually perform the same set of transactions, and the same set of operations, and roll through them that way.
Yeah, but the result set is not something expected. Mixture
Well, I would argue that it should be expected. It may be surprising, but it is the way that it works. But eventually, the highest timestamp will win. For that given column, the highest timestamp is going to win. And like you said, there are ordering things like the delete will get ordered before that. But again, that's if that delete operation is there. So And that's why tombstones, for instance, stay around for 10 days, because that gives that time for things to catch up eventually. Sorry? Yeah, I mean, it certainly is possible. I mean, the idea with it is, though, is that if you have data that would conflict that regularly, you probably should avoid overwriting data anyway, because it's hard to actually come to a even in a system with more advanced conflict resolution, it's hard to even come to a reasonable consensus on the sort of end result of that once the sort of all the updates flush out. So like a good best practice there is to write, append data to what you have, kind of leave the old data where it is, and maybe garbage collect that over a period of time. Sorry.
Yeah. So have you ever run into anybody using, like I know sometimes in high frequency trading systems, they have special like atomic clocks that you could hook into your system to get really good, because the clock could drift using NTP in a local data center. So you have any experience with that?
No, I think if you're trying to do that, then that would be a really bad fit for Cassandra. Again, like if you have that much conflict on data in a concurrent system like Cassandra is designed to be, you should probably avoid that kind of conflict. It's just a best practice in general. I mean, like the stuff that Google's doing with Spanner is really interesting, but Spanner doesn't actually guarantee, like for instance, like globally available writes. Spanner just guarantees that you can perform a read at a timestamp, and guarantees that like if you perform a snapshot read over, instance like if you're doing a big Hadoop transaction or a big Hadoop job, you want data to be stable in that Hadoop job. Spanner can guarantee that. Just so you know, Spanner is this thing that Google came out with where they have GPS clocks and atomic clocks plugged into the servers, and they did some interesting things with it. It's definitely worthwhile reading about.
Yeah, I was just saying it from the sense of like millisecond, or nanoseconds aren't accurate. They go up, they go down.
Right.
So even in Cassandra, wouldn't it be better that we could remove that condition and we could be sure they at least always go up?
Yeah, I think it's impossible to guarantee that they always go forward without having global coordination. Obviously, something like, for instance, like the TrueTime API would be a way to do that. Effectively, the global coordination is the fact that everything all of those systems proceed in the same fashion. But even the TrueTime API that they have in the Spanner paper, which actually talks about this exact problem in detail, can't necessarily guarantee that you'll end up, it can't guarantee that you can't still have conflicting writes. You have to basically have a way to converge that data together. Whether it's last writer wins using timestamps, using vector clocks, using immutable data that doesn't actually have to converge. It's Spanner again is still a dependent on having open communication available, and no partitions for writes. So.
Same question. Yeah, with eventual consistency, it seems like if you're willing to wait long enough, you'll get more consistency. Did you know of any framework or methodology to quantify that?
Yeah, actually, the stuff I was talking about earlier, the hat paper, actually came out from the same sort of the same research group that released this thing called PBS, which is basically a probabilistic way to determine the sort of window of consistency based on network latency and like average, basically statistical things statistics that you collect. Cassandra actually has a way to do this with node tool now. You can say node tool predict consistency, give it some parameters, and it will actually tell you, give you some kind of prediction on that. It's obviously not perfect. It's not a guarantee, but it is a probabilistic, and it can actually tell you it's within a certain percentage of certainty.
One more question?
It's 1.2, sorry.
Sorry, one more question?
One more question.
Anyone over here?
One more.
So how do you feel about CAP and that probabilistic determination versus the systems that say they have like an ordered set of operations, and then but you take into account like real disk failures and outages, do you think like probabilistic consistency on average actually does better consistency than those systems that claim to be really consistent? But when you think about like disks, disks getting corrupt and other scenarios like bit rot are eventually consistent, or distributed consistent, distributedly consistent systems better at that problem?
That's actually a really good point. I guess in a way, yeah. I mean, if you, for instance, a system like Paxos has 3 replicas of data or more, a system like Zookeeper rather has 3 or more replicas of data. I mean, that would make it less likely to be subject to solar flares and things like that, and like you said, bit rot and disk failures. There's still so many it's the whole Byzantine generals thing. There's so many ways that things can go wrong that. Often the things that you don't predict, but as far as like a system like, are you asking like whether, regardless of consistency, a system that's fully distributed probably will have a larger likelihood of surviving through things like disk failures? I mean, the more replicas you have, the more likely it is you can resolve conflicting issues and things like that if you set things up right.
Standpoint, how is the replication going to keep up with not necessarily just the most recent copy of the record, but versions of that record as it moves forward in time? Does that sort of change the whole ACID discussion about locking records and locking a version of a record? And so, is there any consideration in this replication for that kind of topology?
So, which replication are you talking about?
So, when we're talking about Cassandra, we're talking about the records that are being sort of kept at multiple nodes, right? So, there's this whole concept at play when we're talking about temporal data of versions of a record for an interval of time, right? So. In that respect, a lot of the issues that arise around locking an asset around that record come from also the consideration of the version of the record that has to be locked. Internally in the engines, everybody's sort of struggling with this issue, and I just wondered if Cassandra in the replication topology is also considering this, because it's actually coming out as like a SQL 3 standard as well on the
I'm actually getting a cutoff.
Oh, okay. Yeah.
We can take this offline. Thank you guys so much. Again, I'm available for questions.
We can answer these questions in the Meet the Experts room on the 8th floor. Speakers will